All right, very practical, very fun. Today we're going to talk about endothermic and exothermic reactions. Before we do that, let's talk about the mechanism for this process. Here on your screen, once again, we've got a familiar looking balloon, I'm sure. We've discussed this reaction a few times, the reaction between hydrogen gas and oxygen gas to make water. Now, when a chemical reaction occurs, you and I have alluded to this before, there are a few things that have to take place. For these hydrogen and oxygen molecules, these bonds have got to be broken. And it takes work to do that. It takes energy to break those bonds apart. Then, when we form the water, we've got to make these two bonds over here. When chemicals make bonds between one another, when atoms bond, they actually release energy. The amount of energy absorbed and released by the two halves of a chemical reaction usually are not the same. So sometimes reactions require energy to go forwards. They must absorb energy from their surroundings. Other times, when they finish, there'll be an excess of energy, and so they will release that energy. What I'm talking to you about is the concept of endothermic and exothermic reactions. Endothermic and exothermic reactions involve the absorbing or releasing of heat, or thermal energy, during a process. Endo, exo, how can you remember those two things? Endo, the word, sounds quite a lot like enter. In these reactions, heat is entering the reaction. It's being absorbed from whatever is surrounding it. And this means to an outside observer like you or me, if we put our hands on an endothermic reaction, it would feel cold as it was absorbing the thermal energy from us. What's the alternative? Exothermic. Exo sounds an awful lot like exit. In these reactions, heat is exiting the reaction. It releases that heat. In these cases, if you were to touch them, because that reaction is releasing that heat, they would feel quite hot. So again, an easy way to remember, endo, heat is entering the reaction. Exo, heat is exiting the reaction. Not too bad? Naturally, let's have a look at a few examples with these. I'm going to start with the more common one. I'm going to start with exothermic reactions. You might be able to think of one or two examples from just around your day-to-day life of exothermic reactions. We're going to have a look at quite a famous chemistry example right now. So, as you can see, a very exothermic reaction, lots of heat energy being released. If you look at the slow motion very carefully, you may even be able to see just a hint of lilac, almost a purple colour, and that's coming from the potassium that's in this mixture. The potassium will give off a slightly purple flame. Might be a little bit shrouded by all the other fun going on, but this is an example of an exothermic reaction. Let's have a look at how we show that when we're communicating with one another, when we're writing our chemical equations. So you can see down the bottom of the page here, I have a chemical equation to show the reaction that's taken place. So I've got my potassium permanganate reacting with glycerol, and it's produced a series of products here. But in particular, you may notice the addition of something new at the end of that equation here. You can see that delta H. Delta H is referred to as the enthalpy of a reaction, which is a measure of some of the energy changes that take place during a chemical reaction. For many systems, not for all, but for many, it directly represents the amount of heat or thermal energy absorbed or released by the reaction. In particular here, you can see the little negative sign in front of the number. That negative sign means that this reaction has lost energy or given it away. Energy has been released. So if the enthalpy is a negative value, it tells you you have an exothermic reaction, that energy is being released. So again, lots of examples of exothermic reactions out there in the lab and in the world. If we're doing demonstrations, we could do something quite subtle. For example, we could try and add a few drops of sulfuric acid to a test tube that contains water. If I put my hand on that, I can feel it getting warm, or I can pop a thermometer in there and you can see the temperature rising. Or I could do something a little bit more extravagant. I could take a beaker containing some sugar and pour some concentrated sulfuric acid in and watch as the sulfuric acid dehydrates the sugar in a highly exothermic process. You can probably see the heat coming off this reaction. Or I could go one step further and do something else fun. We could take some hydrogen peroxide and then accelerate its decomposition into water and oxygen gas. This, apart from being a visually spectacular experiment, is also an example of an exothermic reaction. If you look carefully amidst the fun, you might be able to see some steam coming off the top of this reaction. So once again, a good example of an exothermic reaction. And we can keep escalating this idea further and further and further until we reach this inevitable outcome. Sadly, wasn't allowed to replicate this for the video. So, they're exothermic reactions. What about the alternative? What about endothermic reactions? Can you think of an example in your day-to-day life of an endothermic process? This usually gets people thinking about it just a little bit more. Ice melting is an example of an endothermic process, but a bit difficult to visualize how that might work out. Photosynthesis is also an endothermic chemical reaction, but again, a little bit difficult to visualize that energy being absorbed. So what I thought I'd do for you is do an experiment where we really can visualize this process taking place. So we're going to do an endothermic reaction together right now. Back into the lab. What I have here is a beaker. I'm going to wash down the bottom, put some water on the mat as well, make sure it's all nice and clean. And then I'm going to pour one white powder, a solid substance, into that beaker. To that, I am then going to add a second white powder, a second solid substance. Then I'll pick up my spatula and just mix those two together. Now there's a couple of unusual observations occurring here. First of all, I've mixed two solids together and they're turning into a liquid. It's not something you see every day, so there's that. You can't experience this from where you are, and you'd probably rather not, but there's also a pretty awful smell emanating from this beaker. We're going to have a look at that in a moment. But finally, you'll notice that the beaker has completely stuck to the mat that it's sitting on. It has frozen onto the mat that I'm sitting on. How has this worked? This reaction is an endothermic reaction. It needs energy. It has to absorb energy from its surroundings in order to proceed. The water that I sprayed on the beaker and on the mat is the energy that it requires. It absorbs the heat from that water and in doing so freezes the water. So it's actually frozen this beaker solid onto the mat. And with my hand around it, I can feel this is actually very, very cold. So this is a visual demonstration of an endothermic reaction. Again, if we have a little bit of a closer look at the chemical process taking place, so I'm mixing a barium hydroxide octahydrate is the technical name if you want to impress your friends, that first chemical. We've got ammonium thiocyanate for the second one. And again, the all-important part of this chemical reaction, that enthalpy, you can see that now it has a positive enthalpy value. And that means that for this reaction to proceed, it has to take in energy. It needs more thermal energy in order for it to proceed. In case you're interested, that awful smell, that was the NH3, the ammonia gas. Lovely. Right, so as we bring this topic to a close, we've discussed endothermic reactions and exothermic reactions. Endo and exo, where heat enters and exits these chemical reactions. How do we show that in a chemical equation? We quote an enthalpy at the end of the reaction, where a positive enthalpy means that we're absorbing energy. It means it's an endothermic reaction. And if that enthalpy is negative, then energy is being released by that reaction. It's an exothermic reaction. How's your hunt for good chemistry jokes going? Endothermic reactions, I was studying before they were cool. Try next time.